Welcome back, everybody. I hope you all had a great break. We're going to jump right into it and start talking about electricity, which is one of my favorite subjects in physics. So, electric charge, what is it? Well, charge is one of the fundamental properties of nature. Charge comes in two types, positive and negative. And we know that like charges repel and opposite charges attract. Some of this stuff should be very familiar to you from chemistry. We know electrons in an atom have a negative charge, and protons in an atom have a positive charge. Protons and electrons attract each other, and electrons repel other electrons while protons repel other protons. When an object has equal amounts of positive and negative charge, we say there is no net charge, and we call it neutral. So if we look at this picture over here, if we have a plastic rod that it has a negative charge and we bring another negatively charged rod toward it, we know that likes repel, so this rod is going to want to move away. Same with if we have two positive rods. A positive and a positive are like, they repel, they want to get away from each other, so this rod will repel. But if we have a negative and a positive, opposites attract, so these are going to want to come closer to each other. Now, just because an object is neutral, that doesn't mean it has no charges within it. It just means that the positive and the negative are balanced. So a good example of this is a polar molecule. Hopefully you remember this from last year too. Water is a polar molecule. The hydrogens in water like to have a positive charge. And the oxygen in water likes to have a negative charge. But an overall water molecule is neutral. The charge is equal to 0. And that's because we have two positives here and two negatives here. Just because if we split this down the middle, this side is overall positive, this side is overall negative, and this side is overall positive, that does not mean that it has a charge. The positives and the negatives end up canceling each other out here. So a water molecule is overall neutral, but within it, it still has charges. So electric charge in the atom. I already mentioned this. The nucleus has protons in it, so it is positively charged. And electrons are negatively charged. These two things attract each other, and these two things will repel each other because they have like charges. So overall, an atom is electrically neutral. If we just take an atom and we leave it alone, it's neutral. It has the same number of protons and electrons. In order to give that atom a charge, we have to add or remove electrons. And this is the key. It's very, very important to remember that only electrons move. Protons never, ever move to create a net charge. And that's because if we look at this picture of the atom, these electrons are way out on the outside. They're free to move. It doesn't take a whole lot to pull them off or add them. But the protons are stuck within the nucleus, and this is a very, very small but pretty massive object. They are stuck there. It takes incredible amounts of energy to move those protons and remove them from the atom. So it's very important to remember, only electrons move. Protons do not move to create a charge. So one way to cause a charge in an atom is to rub two objects together. When we rub objects together, electrons move from one object to the other. So in this picture, we have a ruler and a cloth. And the ruler has the same number of positives and negatives to begin with. Same with the cloth. It has an equal number of positives and negatives. So it is neutral. But when you rub them together, what happens is the electrons are pulled from one object to another. So let's say the electrons are moved from the ruler to the cloth. that means we get left with overall positive charge on the ruler. The protons didn't move from the cloth to the ruler to make this positive charge. The protons stayed where they were. It's the electrons that left that made this overall positive charge. So the electrons moved from the ruler to the cloth, leaving us with an overall positive charge. If two objects are rubbed together and one gains a positive charge, which means it lost electrons, so I'm going to write that. Gains a positive charge means lost electrons. And by the way, the symbol for an electron is a lowercase e with a negative sign. So if two objects are rubbed together and one gains a positive charge, the other object will gain a negative charge of the same magnitude. So gain a negative charge means it gains electrons. And it has to be of the same magnitude. And this is really, really important. This tells us that the total amount of electric charge produced in any process is 0. And this is our law of conservation of electric charge. This tells us that we can never create negative charge out of nothing or create positive charge out of nothing. The only thing we can do is move electrons around. So if I have an object that has 2 protons and 2 electrons, I cannot just add another electron here. That is no good. That breaks the law of conservation of electric charge. What I can do is I can eliminate or move some of these electrons away to create an overall charge. Or I can add an electron from another object to create an overall negative charge. If one region of an object gains a positive charge, there has to be an equal amount of negative charge somewhere nearby. And there is no exception to this rule that has ever been found. So the same number of electrons you start with, you end with. The only thing that we can do to create a charge is move them around. You may remember this name from last year, Robert Millikan. He performed an experiment using oil drops and an electric apparatus to determine the charge on an electron. So before Millikan, scientists knew that electrons had a negative charge, but they didn't know quite how big that negative charge was. So he did his oil drop experiment to determine this. And he found that charge is quantized. And quantized is a fancy word meaning it exists in exact units. So we can have 1 electron, and we can have 2 electrons, but we can never ever have 1.5 electrons. We can only have whole numbers of electrons, which means we can only have whole number multiples of its charge. A unit of charge is symbolized by the letter E, like I said, and this refers to an electron. An electron has 1 unit of charge, so an object can have 1 unit, 2 units, 3 units, -5 units. -5 would be taking away 5 electrons, but it can't have anything in between a whole number. It can never be a fraction of a unit. So in our international system, charge is measured in something called a coulomb. Coulomb. It's kind of hard to spell, but we just use a capital C. So this is our unit for charge. If I have a single electron, that one little tiny electron has a charge of 1.602 times 10 to the minus 19 coulombs. If I have 2 electrons, I have 2 times 1.602 times 10 to the minus 19. If I have 10 electrons, I have 10 times 1.602 times 10 to the minus 19. I can never have a fraction of this number, though. I cannot have 0.5 times 1.602 times 10 to the minus 19th, because that would be half of an electron, which is not a thing. It is not possible. So let's do a little calculation. How much charge would be present if an object had 5 excess electrons? Well, we know from the previous slide that a single electron has a charge of 1.602 times 10 to the minus 19 coulombs. And we have 5 of those, so we need 5 times the charge on 1. So the total amount of excess charge, if an object had 5 electrons on it, would be 8 times 10 to the minus 19 coulombs, or 5 times 1 electron's worth of charge. It turns out that different properties, or different objects have different properties when it comes to charges. We have 2 main camps of objects. We have insulators and we have conductors. Conductors are mostly what we are going to be messing with in this unit because they allow charge to flow freely. And that means we can very easily transfer electrons from one to another or throughout that object. And these tend to be metals. There are other kinds of conductors. For example, salt water is a fairly good conductor, which is why human beings are such good conductors, because we're kind of just giant bags of salt water. On the other hand, an insulator lets almost no charge flow. So in an insulator, it's going to be really difficult to get it to transfer electrons. And this is most other kinds of materials. Some really good kinds of insulators are rubber, wood is a good insulator, and pure water, which is nearly impossible to find or create, is an insulator. Once you have little ions or little charges from the atoms floating around in that water, it becomes a better conductor. So it turns out that there are not just pure conductors or pure insulators. Of course, there's some gray area, and that gray area is called the semiconductor. And a semiconductor can conduct a little bit of charge, but it takes a little bit to get it to do that. It takes a little bit of energy. So if we look at this picture down at the bottom, in picture A, we have 2 orbs. One of them has a positive charge, and one of them is neutral. Now remember, neutral does not mean it has absolutely no charge. It just means that the positives and the negatives are balanced at this point. If we put a conductor touching those 2 orbs, so for example a nail or anything that's metal, the positive charges that are built up in this one are going to move through this conductor and over to spread themselves out. Remember, likes repel, so they want to get as far away from each other as possible. In order to do that, they're going to evenly spread themselves out throughout this whole system. But if we put a piece of wood on top of those 2 orbs, wood is an insulator. The electrons cannot easily flow through it, so the positive charge will stay right here on this one because it cannot have the electrons coming back over. When you have something that is a conductor, there are a few different ways that you can charge it. The first one is an induced charge. So metal objects can be charged by conduction, and conduction requires contact. That's a good way to remember it, actually. Conduction requires contact. Con and con. So if we have a neutral metal rod, its positives and negatives are balanced at this point, and I want it to become positively charged, what I can do is bring a positively charged object to it and touch it. These positive charges want to get as far away from each other as possible, and in order to do that, they make use of moving electrons. So the electrons that are built up in the neutral rod will move to the positively charged rod, which will leave this one with an overall positive charge. That's what conduction is. If you touch a neutral object with a positive object, it will become positive. if you touch a neutral object with a negative object, it will become negative. So the charge essentially gets transferred and spread out evenly from one to the other. Now, if I were to take away this initially positively charged rod, if I were to take away this one after they touch, this one is not going to become neutral. Not all of the charge gets transferred. It will even out. So if I start with 10 extra positives over here, after I touch the two and pull them apart, each of them will have 5. So that's conduction. They can also be charged by something called induction. And induction is a little trickier. Induction has no contact. So we don't actually touch the objects together to transfer any charge. So in picture A, we have our neutral rod with an equal number of positives and negatives here. And it's connected to this funky looking thing. Most of you probably have not seen this symbol before. And what this symbol means is ground. And a ground is literally that. It is a wire or some kind of conductor that connects your object to the ground. It turns out that extra charge likes to flow to the ground. That's just the natural place that it wants to be. That's its happy place. That's why if you stick your finger in a outlet, the electricity passes through you because you are touching the ground at that moment. You are a fairly good conductor, so the electricity found a path through you to the ground, and it's going to take it. So in order to induce a charge in something, you take a neutral object and connect it to the ground. Once you've done that, you can bring a charged object close to it. And remember, any kind of charges that are the same want to repel each other. So if we have a negatively charged rod here, the electrons that are in our neutral object are going to want to go this way. They're going to want to get as far away from this negative as possible. And what happens when you do that is that the electrons literally leave the object. They take the path to the ground and they escape. You can think of them as being pushed away down to the ground from this negatively charged object that we bring by. If we then cut our connection to the ground, cut our wire right off, the electrons that were in that neutral object have left. And if we lose electrons, that means we end up with an overall positive charge. So the story, to break it down again for induction, is we have a neutral object. You bring a negatively charged object toward it, and the electrons in your neutral object are like, oh no, I want to get away. So they run to the ground. And then if we cut off that path to the ground, they can't come back. And that object has lost those electrons. So that is induction. Induction has no contact. It turns out a non-conductor or an insulator cannot become charged either by conduction or induction. So if I have a block of wood and I rub a balloon on my hair to get a charge on it and I touch that balloon to the block of wood, nothing's going to happen. I also can't connect that block of wood to the ground and bring the balloon near it to induce a charge. Within the atoms inside that wood, there will be a separation. The electrons will be attracted to a positively charged object, and the protons will stay out where they are. So, overall, there will be a charge separation in that wood. But the charges will never actually flow out of that object. So it never becomes charged. It turns out we can discover or figure out the charge on an object by using a very simple apparatus called an electroscope. And this is what an electroscope looks like. It has a metal sphere on the top. And remember, metal is a conductor. And it is connected to some gold leaves. Gold is a metal, it is a conductor, And they use gold because you can get it in very, very, very thin filaments, or thin sheets, I guess. And that will allow them to move when there is a charge on them. Because likes repel and opposites attract. So if we have two kinds of charges on these foils, they will attract. If we have the same kind of charge on both of these foils, they will repel. So we can use an electroscope with either conduction or induction. If I bring a positively charged rod to my neutral electroscope, the positives want to spread themselves out. That means the electrons that are on my electroscope escape. They come up here. And we are left with an overall positive charge. So if we're left with an overall positive charge, these two things are going to repel each other because they have the same charge. If we do it by induction, we bring a positively charged rod very close to the electroscope and not touching it, and that makes our electrons come up to the top because opposites attract. Because our electrons come to the top, the protons are left down at the bottom. We have like charges here, they're going to repel. The tricky thing about this is if you do not know the charge on your object, on your rod, then you cannot tell what kind of charge it has just by doing this. So let me see if I can reword that. You can test whether an object is charged or not through this method. If it is charged in any way, the leaves on the electroscope will repel. If it is not charged, they're not going to move. They're just going to stay where they are because there will be no movement of electrons. But if you charge up an object and you want to know, is this positively charged or negatively charged, this basic method will not work. It just tells you if it is charged or not. In order to determine the charge, you need to first give your electroscope a charge that you know. So let's say we start with our electroscope and we give it a negative charge, and we know for a fact that that charge is negative. That means if we bring another negative object toward it, all those electrons are going to repel. So they get pushed down here, and now the two leaves have more negative charge on them than before. See, there are 3 negative charges here and there are 6 here. Because there is more of a negative charge, they want to get away from each other even more than they did before, and the leaves will spread apart. On the other hand, if we have our negative charge here, let's see, erase some of this, there we go. If we have our negatively charged electroscope and we bring a positively charged object toward it, all those electrons in the electroscope will be attracted. So they're going to move up toward the object. Now we have less negative charges left on our gold foil than we did before, and because there's less of a charge there, there's less of a repulsion. They're not trying to get away from each other quite as hard, so they will come together. So with your electroscope, if you give it a charge and bring an object toward it and the leaves move apart, your object has the same charge as the electroscope. If you have your charged electroscope and you bring an object toward it and the leaves come together, you have an oppositely charged object from your electroscope. And the final thing I want you guys to think about tonight that actually has a lot to do with this is, why is it safe to be in your car during a thunderstorm? Most of you know that if you're outside during a thunderstorm, the safest place for you to be is in a car. But why? I want you to think about that. And I want you to think about it not only in terms of materials being conductors and insulators, but also in terms of how electrons move. We'll watch this video tomorrow and I will give you the answer then. Your homework for tonight is to answer these 3 questions. Number 1, imagine combing your hair. If the comb had a charge of negative 16 times 10 to the minus 19 coulombs afterward, did it gain or lose electrons? How many electrons did the comb lose or gain? And what must have happened to your hair while the comb was gaining or losing these electrons? And how do you know? So answer these questions and have the answers ready to turn in the next time you come into class.